Well, you see, the mechanism is built upon two things. One is one calls scalar fields. This is these objects which are here. And the other is what one calls the gauge fields. The big problem at that time was that one had to find gauge fields that have a mass. And nobody knew exactly how to do that, or not only exactly, nobody knew how to do it, essentially. And the interest of that is because these fields are those which give rise to short-range interaction. That means interaction which act at very small scale inside the nuclei of an atom and things like that. And there was no way to make a theory. And we realized that this could be done if we could put some mass to these fields, which you, when you see that, and when you understand it, you see that you cannot do it offhand. So we invented a scalar field, which is this object with phi, and we did the following thing. We decomposed one of these fields. This field here is what's called a complex field. It means it's a collection of two fields, which can be called phi 1 and phi 2, let's say. And one of these fields gives rise to a condensate that is spread out all over the universe. And it is the interactions between A mu and that condensate which gives the field, which gives the mass to the A mu field. And that gave rise to short-range interaction and could be generalized to give mass to all elementary particles. That is due to this condensate. To detect that condensate, that is what has been done in Cern, you have to find this slightly leftover piece, which is there, which is essentially a particle, which is the particle which was detected at Cern. The other part of the field, that one, is just an object which disappears into that field and is necessary for the consistency of the theory. So that one disappears from the spectrum. One doesn't see it, but it's there to allow this one to sustain a mass which you would not have the possibility if that does not exist. I know this is extremely abstract, but if I have 2 minutes, I can hardly do more.